You know what? Let me get my headphones. Hold on. Okay, I'm going to test the headphones so it's easier to hear. All right, good. So I think the headphones are working. So I should be able to hear you easier with these headphones on than without. Okay, but you were telling me that the recording was not. Okay, so now the recording is on. So I think we're good. Okay, so 4.5 is several important discrete distributions. Okay, right, so I talked about a sample space, right? And so a discrete distribution has to do with that. So let's start 4.5.1. That's called the discrete uniform distribution. Okay. And so just as a reminder, right, a discrete sample space is a sample space that is either finite or in one-to-one correspondence with the positive integers. Okay, so that's the definition of a discrete sample space. So as a reminder, definition, a discrete sample space is a sample space that is either finite or in one-to-one correspondence with the positive integers. Okay, so 4.5.1, the discrete uniform distribution. Consider the experiment of selecting a number at random from the set consisting of the numbers. And so instead of writing the numbers, I'm going to write variables representing them. So the numbers are represented by x1 to xn. Okay, let x be the value of the number selected. Okay, so mathematicians love using variables. Okay, so we're not going to talk about numbers, we're going to talk about variables. Okay, so we're going to, the experiment is selecting a number at random from the set x1 to xn. Capital X is the value of the number selected. If we assume that each of the numbers x1 to xn has an equal chance of being selected, then f of x sub I is equal to the probability that capital X is equal to little xi, and that's equal to 1 over n. 1 over n. And this is for I from 1 to, when I is 1, when I is 2, when I is 3, dot, 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 up to including when I is n. Okay, now let me just finish this up. This probability function is called the discrete uniform probability function / distribution. Okay, so I'll read it out loud. Consider the experiment of selecting a number at random from the set consisting of the numbers x1 to xn. Okay, so you have a set. Containing x1, x2, x3, x4, x5, dot, 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 x n minus 1, xn. Okay, so I did an extra one before the last one. Okay, so you have that set. And so the experiment is selecting a number at random from this set. They're all different. Okay, let capital X be the value of the number selected. Okay, so if you select x5, then capital X would be x5. If you selected x2, capital X is x2. If we assume that each of the numbers x1 to xn has an equal chance of being selected, okay, and so selecting each value is equally likely, that's the assumption, then f of x sub I, which is equal to the probability that the value of capital X is little xi, is equal to 1 over n, meaning the probability of selecting any of them is 1 over n, because they're each equally likely to be selected, and there's n of them, right? So if n things in the set are equally likely to be selected, the probability of selecting any one of them is just 1 over the total n, okay? And so this probability function is called the discrete uniform probability function / distribution. The uniform is because the probability of selecting each of them is the same. That's the idea of the uniform nature of this function, that the value is always the same. It's 1 over n for each thing in the set. Okay, so the probability of x1 is 1 over n. I mean, f of x1 is 1 over n, f of x2 is 1 over n, f of x3 is 1 over n, f of x of n is 1 over n. And so it's called the discrete uniform probability function / distribution. Okay, all right. And so this is an example of that. And so now I'm going to state this formally as a definition. It's a definition. Okay, this is definition 4.3. The function f of x sub I is equal to 1 over n for positive integers n such that I is equal to 1, 2, 3, up to including n, is called the discrete uniform probability function. Okay. This is summing up what was happening above. Okay. This is the function where you're choosing an element x sub I from the set x1 to xn. And the probability of choosing any of the elements in the set x1 to xn is 1 over n, because we're saying that the probability of each is equally likely. Okay, and so this is called the discrete uniform probability function. It's defined on a set of elements. It's defined on a set with n distinct elements. And it says that the probability of choosing each value is the same, 1 over n. That's the discrete uniform probability function. Okay, a random variable, capital X, has a discrete uniform distribution / function, and is a discrete uniform random variable if and only if its probability function is the discrete uniform probability function. Okay, and so if you're in an experiment where the probability function is a discrete uniform probability function, that will tell you that your variable is a discrete uniform random variable, and that you have a discrete uniform distribution for that random variable. Okay, now this is if and only if, right? And the logic of an if and only if statement is saying that the first thing, this thing, is equivalent or has the same truth value as the other thing. So this is a statement of its own. This whole long sentence is one statement that says the first underlined statement is the same truth value as the second underlined statement. They're both true or they're both false. And so that's what if and only if means logically. Okay, now once you understand the logic of the statement, you can then know what it's saying. If you don't understand the logic behind a sentence or a statement, then you can't make sense of what it's telling you, right? So first you have to understand the meaning of if and only if, that this underlined statement, substatement, it's saying this underlined substatement has the same truth value as that underlined substatement. and then you can understand what each statement means, and then you can say, okay, those two statements have the same truth value. That's what I'm saying there. Okay. So next is 4.5.2, the Bernoulli distribution. Bernoulli distribution. Okay. So let's consider an experiment with exactly and only two possible outcomes, either success or failure. Okay. Okay. Such an experiment is called a Bernoulli trial. So when you conduct an experiment where there's only two possible outcomes, success or failure, that's called a Bernoulli trial. If capital X is a random variable that takes on a value of 1 when the Bernoulli trial is a success, and a value of 0 when the trial is a failure, then capital X is a Bernoulli random variable. So what's happening is this random variable capital X is capturing the idea that there's only two possibilities. Okay, and so this is the meaning of a Bernoulli random variable. Okay, you either have success or failure in your experiment. Okay, and so when your experiment is a success, your random variable will spit out the value of 1, and when it's a failure, it'll spit out the value of 0. And so X in that case is called a Bernoulli random variable. Okay. Remember, a random variable is a function where you input outcomes of an experiment and it outputs a number. Okay, and so if you have an experiment where you only have success or failure, then you're separating all the results, all the outcomes of your experiment into successes and failures, right? And so whenever there's a success, you input an outcome that's an excess, that's a success, you output a 1. When you input a failure, the output is a 0. That's a Bernoulli random variable. It's the function where if you input a success, it outputs a 1, and if you input a failure, it outputs a 0. Okay, so the random, even though we're calling it a variable, it's a function. It's technically a function whose inputs are outcomes of an experiment and whose outputs are values defined in some way. Okay? So if P is the probability of success, and Q, which equals 1 minus P, is the probability of failure, then, so I put in words, but I'm going to use an equal sign to make this easier to read. Okay, so P is the probability of success, and Q, which equals 1 minus P, is the probability of failure. Then f of x is equal to this piecewise function, where it's P if x is equal to 1, Q if x is equal to 0. Okay? Okay. So Okay. This probability function is called the Bernoulli probability function / distribution. Okay, and so if your random variable, okay, so if your random variable has value 1, the probability of your random variable having a value of 1 is P, and the probability of your random variable, so the probability of success is P, and the probability of failure is Q. That's what that's saying. Okay, P is the probability of success, Q is the probability of failure. Okay. Right, because this is what's happening here. If f of 1 would be saying it's the probability that capital X is equal to 1. And so that probability is P. Okay? Because capital X is a random variable that takes on 1 when the trial is a success. Because P is the probability of that success. And then f of 0 is the probability that X equals 0. The value of X, your random variable, is 0. This is equal to Q, which is 1 minus P, which is the probability of failure. Okay. So f is a probability function which tells you the probability that your random variable is taking on this value in the parentheses here. F of 1 is the probability X equals 1. F of 0 is the probability X equals 0. Okay, and X is 1. The odds of X being 1 is the odds that your outcome is a success. And the chance of having X equal to 0 is the chance of failure. Make sense? And since the probability of success plus the probability of failure is 1, there are only 2 choices. The probability of failure Q is 1 minus P. Okay. So a random variable, capital X, has a Bernoulli distribution and is referred to as a Bernoulli random variable if its probability function is the Bernoulli probability function. Okay, so if your probability function is this Bernoulli probability function, then you can say you have a Bernoulli distribution and you have a Bernoulli random variable. Okay, let's keep going. 4.5.3, the binomial distribution. Okay, so consider n Bernoulli trials. Okay, so each trial, again, it's called a Bernoulli trial. Each trial is an experiment whose only outcomes are success or failure. Right? If S sub n is equal to the total number of successes in the n Bernoulli trials, what is the probability function of of S sub n. Okay, so consider n Bernoulli trials. If S sub n is the total number of successes in the n Bernoulli trials, what is the probability function of S sub n? I will explain this. Okay, in other words, what is the probability P of S sub n equaling to little x for, and it is a probability. What is P, the probability of S sub n equaling to x for x equals 0, 1, 2, up to including n? So little x are values, and it's not the capital X, the Bernoulli random variable, right? Little x is the notation used to just represent values, in this case, 0 to n. Okay, so I'm asking the question, what is the probability that the number of successes in the n Bernoulli trials is 0? Or what is the probability the number of successes in n Bernoulli trials is 1? Or what is the probability that the number of successes in n Bernoulli trials is 2? Okay, so to explain this notation, look at the following. So I'm not yet solving the problem, I'm just explaining what I'm asking. So, so P of S sub 3 equaling to 5 would be, oh, no, wait. Make that a 3, sorry, make this a 5. Okay. P of S sub 5 equal 3 would be equal to, well, S sub n is the total number of successes in n Bernoulli trials, right? S sub 5 is the total number of successes in 5 Bernoulli trials. And so this is equal to the probability that the total number of successes in n Bernoulli trials is 3. Okay. I could have written that a little shorter, but I wanted it to, the words to match a little bit more the notation. So P of S sub 5 equals 3 is equal to the probability that the total number of successes in n Bernoulli trials, in 5 Bernoulli trials is 3. Written a little bit simpler, but just a little different than the math notation, is this is equal to the odds that you succeed in 3 out of 5 Bernoulli trials. That sentence is easier to understand, but the first sentence captures more what the notation is saying than the simpler sentence. See? Okay, so P of S of 5 equals 3 is telling you the odds that you succeed in 3 out of 5 Bernoulli trials. Okay? In exactly, I'll put the words exactly. Okay? Is the odds that you succeed in exactly 3 out of 5 Bernoulli trials. Okay? So it doesn't matter the situation you're talking about. You could be talking about an experiment, one experiment that you're describing as a sequence of Bernoulli trials. And you could be talking about something completely different. And these probabilities you're going to discuss are the same because you're just talking about the number of successes, where each experiment is success or failure. And so what success, how you define success and failure doesn't change the odds of a success or failure. Okay, so this is another instance where in probability we're talking about general probabilities, and these general probabilities actually apply to many situations. So when you calculate these probabilities, you actually can apply them to many different diverse situations in order to capture the odds of completely different things happening. Okay? Okay. So the P of S of 5 equals 3 is the probability that the total number of successes in 5 Bernoulli trials is 3, which is equal to the odds that you succeed in exactly 3 out of 5 Bernoulli trials. Okay, so that's an example, that's explaining the notation. But I want to answer this question still. What is the probability function of S sub n? What is P of S sub n equals x for these values of x? Okay. Okay, so let's go back to our original question. Okay, this question: what is p? What is p of s of n equals x for x equals 0 to n? Okay, and so we're going to answer this question in steps. So this is step 1. What is the probability of successes in the first x trials, and then failure in the remaining n minus x trials? Oops, sorry. So what is the probability of successes in the first x trials and then failure in the remaining n minus x trials? Okay, and so to answer this question, we're going to introduce some simple notation and then get some simple answers. Okay, so let s sub I equal to the event of success in the nth, in the ith Bernoulli trial. Okay, and let f sub I be equal to the event of failure in the ith Bernoulli trial. Okay, so S sub I is success in the ith Bernoulli trial. Capital F sub I is the event of failure in the ith Bernoulli trial. Okay, now let's find the probability that we just are talking about, right? What is the probability of success in the first x trials and then failure in the remaining n minus x? And so if you're succeeding in the first x trials, then you have S sub 1, S sub 2, S sub 3, ... S sub x. See, you're succeeding in the first x trials. So you've succeeded in the first and the second and the third and the fourth, ... and the x. And then failure in the remaining n minus x. And so the remaining n minus x means that you've now failed in the next one. After the x trial, you now start failing all of them. So capital F sub x plus 1 means that, well, so first you succeed in the first x trials, then the very next one you fail. So it's capital F sub x plus 1. Then you fail again. So then you keep failing. And then capital F sub x plus 2. And then you fail again. Capital F sub x plus 3. And so you keep failing. And then at the end, up until including the n. So the remaining n minus x trials. So if the first x trials you fail, and then I mean in the first x you succeed, and then the remaining n minus x you fail, that means there were a total of n trials. Okay, x successes, x little x number of successes, and then from x plus 1 to n, you want to quantify that. If you take x plus 1 to n, where n is greater than or equal to x plus 1, if you take x plus 1 to n, there's n minus 1 n minus x of them. Okay? Or you can think of it this way. You have n at the end, and you start at 1, right? And you're removing the first x. So if you have a total of n, and you remove x, so that's n minus x. That means there's n minus x of these, right? Okay, so this is the situation where you succeed in the first x and fail in the remaining n minus x trials. We want to find that probability. Okay, well, these events are independent events, meaning that the probabilities of their intersections are the product of their corresponding probabilities, meaning, let me write it and it'll make it easier to see. This is P of S1 times P of S2 times P of S3. This is not always true, but in this case it is, because each experiment is completely independent of the other, times P of S sub x times P of F sub x plus 1, ... times P of F sub n. Okay, Actually, I'm going to put one in between here. This is P of X, P of F sub X plus 2. Okay, so you succeed in the first X and then you fail in the remaining N. But then each of these events are independent, which means that the probability of all of them happening is the product of their respective probabilities. Okay, like if you flip a coin twice, right? If you want to know the probability of getting 2 heads, well, you could say the probability of getting 2 heads is the same as the probability of getting the first head times the probability of getting the second head. Okay, because each coin flip is an independent event. Okay, and the reason they're independent is because the occurrence of one has no effect on the other. Okay, when you get heads or tails in the first flip, it doesn't affect whether or not you get heads or tails in the second flip, right? It makes no difference what the first flip was. The second one will have the exact same odds of being heads or tails. So here, when you have success or failure in each Bernoulli trial is independent of the other one. And so if you succeed or fail in the first trial, it does not affect at all the chances of success or failure in the second trial. Okay, each trial is independent of the other one. And so in this one, we want the probability that you succeed in the first X and then fail in the next N minus X Bernoulli trials. So that probability is equal to the probability of success in the first trial times the probability of success in the second times the probability of success in the third times dot, 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 times probability of success in the X trial times probability of failure in the X plus 1 trial times probability of failure in the X plus 2 trial times dot, 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 times probability of failure in the Nth trial. Okay? And so now you see it's a product of these probabilities because each trial is independent of every other one. And so now that product is equal to, well, P, little p is the probability of success, and Q is the probability of failure. And so what we did in the first thing is we took P and we multiplied it X times, right? And then we took that product and we multiplied it by the probability of failure, N minus X times. See that? So there's X successes and N minus X failures. So there's X successes and N minus X failures. And so this is equal to the product of, so this is equal to P to the X times Q raised to the N minus X power. Okay, and so that's because there are little x of these, and there are little q of these. Okay, and so since there's little x p's and there's little there's n minus x of these, then it's p to the x times q to the n minus x. That's the probability of success in the first X trials and then failure in the remaining N minus X. Okay. Okay, so that's the first thing. Step 2. Okay. Step 2 is okay, so remember the original question is, what is the probability of S of n equals X for each of these values, right? Probability of exactly X successes. And so you have one instance of exactly X successes and N minus X failures, exactly X successes. But this is only one ordering of those trials. You can rearrange the trials in which there were successes and failures. And that's another instance of exactly X successes. So step 2 is find all the ways to arrange X successes in N Bernoulli trials. Okay? So we have a simple combinatorial representation of that situation. if you have a total of n trials, there's n choose x many ways. This many ways, this is the number of ways to succeed in exactly x of the n trials, Bernoulli trials. See that? You're just choosing x of the total n to be successes. And choose x is that combinatorial number represents the total number of ways to arrange x successes in n Bernoulli trials. Okay, each of those ways has a p to the x, q to the n minus x chance of happening. Okay, so p to the x times q to the n minus x. So each of those arrangements of exactly x successes has that probability of happening. Okay, and so the value of p of s sub n equaling to x, the probability that in n Bernoulli trials you have exactly x successes, is equal to the number of ways you can choose x of those trials to be successes out of the total n, times the probability that for each choice of exactly x successes has a p to the x, q to the n minus x chance of being a success, x successes. That's the probability. Okay. And so that's the answer. And this is for all values that we were considering. So this is for x equals 0, 1, 2, 3, 4, ... up to including n. Okay. This probability function is called the binomial probability function. Okay, I'm going to go to the whiteboard now and just explain this a little bit again. So let's say you have 3 Bernoulli trials. Okay, so let's say you have 3 Bernoulli trials. So each Bernoulli trial you can succeed or fail, right? P is a probability of success, Q is a probability of failure. And so let's ask the question, what is the probability that S sub 3 is equal to 1? What is the probability that in 3 Bernoulli trials you have exactly 1 success? Okay, well, just like in our example, let's say that we succeed on the first trial only. Then, I want to use a different color here. So you succeed in the first one, and that probability has P, little p probability of success, and you fail in each of the next 2. So in order to find the probability of succeeding in the first one only, and then failing in the next 2, that would be P times Q squared, right? That would be P to the first power times Q to the total 3 minus 1 power, which is 2. Q squared, right? But Q squared is from 3 minus 1 because it's a total of 3 trials. And if you succeed in 1, you fail in the total 3 minus the number of times you succeed 1. So the number of failures is the total number of trials minus the number of times you succeeded. That's 3 minus 1. Okay? So succeeding in only the first trial means that P times Q times Q. That's the probability of succeeding in the first one. Okay, that's P times Q squared. Okay, so this is P times Q squared. You get the 2 from 3 minus 1. Now, that's only if we if the place we succeed is the first trial, right? We want the probability that we succeed exactly once in 3 trials, but it doesn't have to be the first trial where that 1 success happens. And so actually there are 3 ways in this instance where we could succeed in one of the trials, right? We could have succeeded in the first one, like we just talked about. we could have succeeded in only the second one, or we could have succeeded in only the third. That means that since there's exactly one success, all of the other 3 minus 1, which equals 2 trials, is a failure. And so now in each of those instances, we get the same probability. Q times P times Q is the same as P times Q times Q, right? So in each of these rearrangements of successes and failures, we get that the probability is P times Q squared. See, we get P times Q squared here, P times Q squared here. So the common probability is P times Q squared, succeeding once and failing twice in 3 Bernoulli trials. So the probability of success, the probability of exactly one success in 3 Bernoulli trials, this thing, is equal to, well, what's the probability of succeeding in the first one and failing the rest? That would be P times Q squared. That's the common probability that each arrangement has of successes and failures. And then, well, how many ways can you rearrange that P? How many ways can you rearrange the successes and failures? That's 3 choose 1. You have 3 trials, and how many ways can you choose one of them to be a success? 3 choose 1. That's 3. And so the probability of success, exactly one success in 3 Bernoulli trials, is 3 choose 1 PQ squared. Okay, this is an example of the more general expression that we just talked about. The probability of S sub n equals X is equal to, the 3 is the n here. You have n Bernoulli trials. You want to choose X of them to be a success. So if X are successes, you're multiplying P by itself X times. And then if you succeeded X times, but there's a total of n trials, the n minus X remaining are failures. That's n minus X there. See that? Okay, and so what I illustrated here in this simpler example is a more general concept that we just showed, that this probability is equal to this. And these are for values of X from 0 to n. Okay, and so this is for X. This is for X equals 0 to n. Okay? And so that's the thing I was talking about on the Word document. Make sense? Oh, okay, good. Thank you for saying that. That's good. So now I know that it's making sense. Okay, good. Okay, definition 4.5. So definition 4.5. Let little n be a positive integer, and let P and Q be probabilities with P plus Q, P plus Q equal to 1. The function P plus Q equals 1. The function B of X colon n comma P is equal to this thing, n choose X times P to the X times Q to the n minus X for X equal to 0, 1, 2, 3, and so forth up to including n. This is the binomial probability function. Okay, so this is definition 4.5. And it's the definition of the binomial probability function. Okay, So in our previous example, P was the probability of success, Q is the probability of failure. And so that's what we will usually think of them as. But more generally, P and Q are just probabilities that add up to 1. And this function is using those two probabilities. And so this is called the binomial probability function. Okay, a random variable has a binomial distribution and is referred to as a binomial random variable if its probability function is the binomial probability function. So here we're talking about a binomial random variable. Okay, so if you have a random variable whose probability function is the binomial probability function, this guy, then your random variable is actually a binomial random variable. That's what it's called. Okay, this is just talking about like terminology and stuff. It is a little annoying to think of this terminology. B of x colon n comma p is equal to b of n minus x comma n comma 1 minus p. Okay, so here's a note here that these two values are the same. Okay, so I can talk to you about why those two are equal, but before I do that, I actually just want to calculate it so that we get a sense of what this function is saying. Okay, so let's do that first. Okay, so we have this definition here, and let's see an example where we calculate it so that it makes more sense. Instead of thinking, before we think more generally, let's look at a concrete example. So example 4.7, part A, find the probability of getting exactly 4 heads in 10 flips of a coin. Okay, so this probably looks a little bit like the test question you just had, right? But in that question, it was only exactly 1 heads, okay? Or at most 1 tails, I think it was, right? So you're able to break it up into 2 very specific instances or 1 specific instance, right? So this question, it looks the same and it's almost the same, but this is taking the generality a little bit further, okay? We only have to deal with 0 with 1 heads or 0 tails, 0 or 1 here. This is 4, so this is a bit of a different question. Okay, so we want to find this probability. So the probability of exactly 4 heads in 10 flips. So the probability of exactly 4 heads in 10 flips. Well, this is the probability of S sub 10 equaling to 4. Okay, so if you understand the notation very well, then a lot of probability problems come down to just writing down the notation correctly. Okay, so in this instance, if you can write this notation, even though it's weird, if you can understand the notation, then once you write down the notation, this is just a calculable value, and you calculate it, and that's the answer. So let me explain again the notation. You want to find the probability of exactly 4 heads in 10 flips of a coin. Each flip of a coin is a Bernoulli trial, where there's either success or failure of getting a heads. Okay, so we're defining success as getting a heads on a coin flip. So you flip the coin 10 times, and each coin flip is a Bernoulli trial because there's either success or failure at getting heads. If the coin flips heads, you succeeded at flipping heads. If it flips tails, you failed at flipping heads. Make sense? Okay. So this experiment, you can think of this experiment as 10 Bernoulli trials, where success is defined in each one as flipping heads. And then the probability of exactly 4 heads in 10 flips is the probability of 4 successes in 10 Bernoulli trials. See that? The probability of exactly 4 heads in 10 coin flips is the probability of exactly 4 successes in 10 Bernoulli trials. The success in we're defining success in this case to be heads. Make sense? So we want to know the probability of S of 10 equal to 4. And so you don't even have to think about flipping coins anymore now. You now see the experiment as just being 4 successes in exactly 4 successes in 10 Bernoulli trials. Well, how do you calculate that probability? Well, what you have to do is if you have 10 Bernoulli trials, then how many ways can you choose 4 of them to be successes? It's 10 choose 4. Okay. Well, what's the probability of success? The probability of success is 1/2 because each coin flip has a 1/2 chance of being heads. And so how many successes? We're talking about 4 successes. So it's 1/2 to the 4th. You multiply the probability of success, which is 1/2, 4 times, 1/2 to the 4th. Then take the probability of failure, which is also 1/2 because there's a 1/2 chance it's tails for each flip. That's 1/2. And so if you succeed 4 times and there's 10 flips, that means you have to have failed 6 times. Okay, so I don't need to tell you how many times you don't flip a heads, right? If I'm telling you how many coin flips there are, and I'm telling you how many head flips there are, then you can deduce from that how many tails there are, how many failures there are. So there are also 6 failures, even though it wasn't said. Okay, so the probability of exactly 4 successes in 10 Bernoulli trials is 10 choose 4 times 1/2 to the 4th times 1/2 to the 6th power. It's 1/2 to the 4th times 1/2 to the 6th is the probability of succeeding in the first 4 flips and then failing in the next 6, right? 4 plus 6 is 10 flips. That's the probability of succeeding the first 4 and then failing in the next 6. But every rearrangement of successes and failures also has that probability. You've succeeded 4 times, failed 6 times. 1/2 to the 4th times 1/2 to the 6th. And so how many ways can you, again, arrange those 4 successes in 10 trials? 10 choose 4. And so you're adding that probability I had bolded, 10 choose 4 many times. It's 1/2 to the 4th times 1/2 to the 6th plus 1/2 to the 4th times 1/2 to the 6th plus 1/2 to the 4th times 1/2 to the 6th plus dot, 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 and so forth. But you add 10 choose 4 of them. And so then instead of adding them, you multiply it by 10 choose 4. And so when you do that, you calculate that and get that's equal to 0.2051. Okay? That's the probability of exactly 4 heads and 10 flips of a coin. Okay. And what's cool about it is you calculate it and you don't even have to think of the experiment anymore. Okay. B, find the probability of obtaining exactly 12 sixes in 20 throws of a die. Okay. So you throw a die 20 times. Okay. And you want to know, well, what's the probability that exactly 12 of them are 6s? Okay. Normally, you might say, okay, I think I could do this, but if I have like 10 hours, I can sit down and I can think of all the ways to throw dice, and then I can like add up, right? It would take a really long time, right? You might think that you can get this if you're given a really long time, but you can actually do this really fast now. So the probability of exactly 12 6s in 20 throws of a die. So just armed with combinatorics and and Bernoulli trials and all that. We're going to do this quickly. So you throw the die 20 times. Each die roll is a Bernoulli trial. So your first thought is, well, wait a second, there's 6 sides to a die, right? So how could it be a Bernoulli trial, right? There's 6 sides to a die, there's 6 outcomes. There's 6 values the die could roll, right? So how could it be a Bernoulli trial? But the goal is to either roll a 6 or not roll a 6, right? We want to find the probability of exactly 12 6s in 20 throws of a die. So in each experiment, you either succeed at throwing a 6 or failing at throwing a 6. And so that's how it's a Bernoulli trial, right? So it's not a Bernoulli trial because there are two outcomes in your experiment. It's a Bernoulli trial because you've separated the outcomes into two groups. The outcomes which are success and the outcomes of which are a failure. In this experiment, we've chosen to think of rolling 6 as a success and 1 through 5 as a failure. And so that's how rolling a die, even though it has 6 outcomes, it's still a Bernoulli trial where there's only success or failure. Okay? So you roll a 6 as a success, 1 through 5, it's a failure. Okay. So now what is the probability of that? So first you can ask the question, well, you have 20 throws of a die, and you want 12 of them to be a 6. So how many ways can you choose 12 of the 20 experiments, 12 of the 20 Bernoulli trials, 12 of the 20 dice rolls to be a success? That's 20 choose 12. Okay, so that's the number of ways of arranging your 12 successes in 20 trials, Bernoulli trials. Now, in each choice of those arrangement of 12 successes and 8 failures, for each of those choices, they each have the same probability. What is that probability? Well, you're saying you've succeeded at rolling a 6 12 times. So that probably is 1/6 raised to the 12th power, right? Rolling a 6 successfully has a 1/6 chance of happening. And then you want to do that 12 times. So it's 1/6 to the 12th power. Each experiment, each trial is independent of the other. And so you just multiply the probabilities, right? And so 1/6 to the 12th, that corresponds to the 12 successes. There's 20 throws, so 12 successes means 8 failures. And so you failed the other 8 times. And so the probability of not throwing a 6, the probability of failing at throwing a 6 is 5/6, because 1, 2, 3, 4, and 5 are not 6s. And so those 5 out of the total 6 dice rolls are failing to get a 6. So that's 5/6 for failure. There's 8 of them. That's 5/6 to the 8th power. Okay, and so now 1/6 to the 12th power times 5/6 to the 8th power. That's the probability of succeeding in the first 12 dice rolls and failing in the next 8 of throwing 6s. Okay, and then there's 22 12 ways of arranging those successes, that many successes and failures. And so the probability we want is 22 12 times 1/6 to the 12th power times 5/6 to the 8th power. And that equals, you calculate that, you get 0.0000135. And that's the value. Okay? So the probability of obtaining exactly 12 6s in 20 throws of a die is 0.0000135. Right? Okay. So it's not that difficult. It can be a little tricky. When you start this class, the class is it's not that hard. Maybe. I don't want to say it's easy if you're finding it hard. Some of the concepts are kind of easy, but we can take an easy problem, and you can see how it can get a little bit more difficult when we make the numbers bigger, right? Okay. And so if you did this with 3 throws of a die, it'd be kind of easy. Once it's 20, once you're rolling the die 20 times and you're thinking of exactly 12 6s, suddenly you need these more abstract ideas to calculate them, right? Without getting a headache. Okay, so with these abstract ideas, we can now think of really, really big situations, and we can get answers very quickly. Okay, so example 4.8. Example 4.8. Okay, so if the probability of recovery from a certain disease is 0.20 and 10 people came down with the disease, what is the probability that at most 3 of them will recover? Right? So every time I think of this problem, it's kind of sad, because when you think about it, But all the people don't recover, do they die? So the problem doesn't say, but hopefully they didn't die. But okay, so if the probability of recovery from a certain disease is 0.20, and 10 people came down with the disease, what is the probability that at most 3 of them will recover? Okay, so let's compute that. So solution. Okay, so let's write it out. Probability at most 3 out of 10 will recover. Okay, so again, at first this problem seems very difficult. Okay, what is the probability that at most 3 of them will recover? But if you break down the problem, it gets much easier. So the probability that at most 3 out of 10 will recover is the probability that 0 recover plus the probability that 1 recovers, plus the probability that 2 recovers, plus the probability that 3 people recover. Exactly 3 people recover. Okay. There we go. Okay, so the probability that at most 3 out of 10 people recover is probably 0 plus 1 plus probability 2 plus probability 3 recover. Okay, and so if you calculate each one individually and then add up those values, then you found the total probability. Okay, so what is the probability of 0 successes? Well, let's use our binomial probability function. Okay, so let's quickly look back at this definition 4.5, the definition of a binomial probability function. Okay, here we said that if p plus q is 1, then this thing equals this amount, this value, right? This expression is what we use to talk about exactly x successes in n Bernoulli trials, right? The probability of exactly x successes in n Bernoulli trials. And so that's what this value is. That's what this function tells you. It tells you the probability of exactly x successes in n Bernoulli trials, where the probability of success is p. Okay? And if the probability of success is p, that means that the condition is p plus q is 1, which means q equals 1 minus p, and q is probably a failure. Okay? So this notation doesn't talk about q in it, but it's understood from this assumption. From this assumption, you're getting q is equal to 1 minus p, the probability of failure. Okay? And failure is defined from success. And so if you know the probability of success, from it, you deduce the probability of failure because they add up to 1. Okay? So the probability of failure q is 1 minus the probability of success p. That's the meaning of this. Okay? And so I'm going to write that right here. B of x colon n comma p is equal to the probability of success in exactly x Bernoulli trials, in exactly x out of a total of n Bernoulli trials, where the probability of success is p. Okay, that's what that thing is. That's what this thing is in the definition. This thing, it has 3 letters in it: x, n, and p. X is x semicolon n comma p. Okay, this is the probability of success in exactly x out of a total of n Bernoulli trials, where the probability of success is p. Okay, so there's 3 values you need in order to find this value of this function. It has 3 inputs and 1 output. The inputs are x, n, and p, and the output is a value, a number. Okay, so here, so again, we have this, right? We have this expression. So I'm going to copy this and bring this here. So we have this expression from earlier, and I explained it in words as this. So let me bring this here, and copy it, and remind you here. Okay, and Let's do that for now. Okay, so this is how you compute it, and that's what this means. Okay, so if 0 people recover, right, you have 10 Bernoulli trials, right? So you have 10 Bernoulli trials, and so I have 0 recover. Let's call success. Okay, so I figured out how to organize this now. Let's call this side work. So 10. Okay, so 10 people came down with disease. So there are 10 Bernoulli trials. Okay, so success is recovery. Failure is not recovering. Okay. So each person who gets sick, considering whether they recover or don't recover, is a Bernoulli trial. Success is recovery, failure is not recovery. Okay. And it says here that recovery, the probability is 0.20. So that means that the probability of success, which equals P, which equals the probability of recovery, which equals P, is equal to 0.20. Okay. And so that's P. And so there are 10 Bernoulli trials, right? And so that means N is equal to 10. So that's N is 10. Success is recovery. Probability of recovery is 0.20. So P is equal to 0.20. And so the number who recover is X. So X is, little x is the number of people who recover. It's the number of successes, right? The number of successes is X. That's the number of people who recover. So saying 0 people recover is saying that the value of X is 0. And there are 10 Bernoulli trials, and the probability of success of recovery is 0.20. And so the value of the Bernoulli probability function, binomial probability function, the value of this function is the probability that 0 people recover in this instance, in this problem. B of 0, semicolon 10, comma 0.20. It's a probability that 0 people recover out of 10, where the probability of recovery is 0.20. Or it's a probability in 10 Bernoulli trials that you have 0 successes, where the probability of success is 0.20. Plus the value of another binomial probability function. Binomial probability function. And so here, 1 success, still in 10 Bernoulli trials, and still the probability of success is 0.20. We're just changing the number of successes, right? If you change the number of people who recover, you're changing the number of times you succeed, and that's it. Everything else stays the same. The number of trials is the same, and the probability of recovery, the probability of success is the same. So that's plus that. The next one is also B of a value, and the one after that is B of a value also. And so I'm not going to say anything for maybe 30 seconds. I need to finish the lesson, so I'm going to have to say something soon. So I'll give you 30 seconds to just plug in, think yourself what those two are. Okay, so don't say it out loud. Just think about it. What do you put in those two boxes? I saw a question, so I'll answer the question when the lesson's done, just because we already got past that. Or well, let me first finish this. It's better when you ask a question out loud than in the chat, right? Because I don't see the questions in the chat while I'm teaching. Okay, so B of 2 colon 10 comma 0.20. Okay, so this is the probability of 2 successes, 2 recoveries in 10 Bernoulli trials where the probability of success or recovery is 0.20. This is B of 3 colon 10 comma 0.20. Probability of 3 successes in 10 Bernoulli trials where the probability of success is 0.20. Okay, and so you have the values of these 3 binomial probability functions, and you calculate each one, and then you add up their values, and then that's the original probability. Probably at most 3 out of 10 will recover. So what's the value of the first binomial probability function? Well, you want to find 10 choose 0, number of ways to choose 0 out of the 10 to be successes. Then take 0.20, the probability of success, raise it to the 0 power. Then 0.80 is the probability of failure, and raise that to the 10th power. That's the value of the first one, B of 0, 10.2. There's 10 choose 0 ways to choose 0 out of the 10 to be successes. That means you multiply 0.20 times and multiply 0.80 10 times. Okay, the next one, plus, now it's the, so now it's still, now it's 10 choose 1. So you have 10 choose 1, and then it's 0.20 raised to the first power times 0.80 raised to 9th power. Okay, so you choose 1 out of the 10 trials to be successes. So probability of recovery is 0.20, probability of not recovery is 0.80, and then it's, so that's that. So this is a pretty bad, terrible disease. Plus, and so then plus now again, so you have 10 choose 2, okay, times 0.20 raised to the 2nd power times 0.80 raised to the 8th power. That's for B of 2, 10.20. Okay, so I'm going to finish up this lesson quickly, and then a little bit more. And then this is plus 10 choose 3 times 0.20 cubed times 0.80 to the 7th power. And so then that's B of 3, 10.20. Okay, you just calculate each one. And then, so you calculate each one, and then you add them up. And when you do that, you get 0.1074 plus 0.2684 plus 0.3020 plus 0.2013. This is equal to 0.8791. Okay, you calculate each of them separately, and then you add them up, and you get that. Okay, and so that is the end of that example. So next class we will just continue talking about similar kind of problems. So we're going to change it up a little bit. Okay, and so that's it for today. Oh, okay, the side work here. Why is that? Okay, so lesson is done right here. Okay, so somebody asked a question in the chat about this problem. So I'll address that question now. Okay. So you asked Gabriel, you asked the question, how would we approach this problem if we had to roll exactly 12 sixes in a row in 20 throws? Oh, okay. So if you had to throw exactly 12 sixes in a row, then what would happen is it's out of 20, right? So if you had 20 throws and you had to throw exactly 6 in a row, exactly 12 in a row that were sixes, well, then you can shrink down those 12 in a row and think of it as one probability, right? If you had 20 throws of a die, dot, 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 and then this was another one. Now let's say this was 6 in a row. This was 12 in a row. Right, 12 sixes. Then there's 8 other ones, right, that are not sixes. Instead of thinking of, where did the 12 go, just think of that as one individual object. And so you have your 6 throws, you have your 12 sixes where you could put somewhere, and then you have 8 that are not sixes. Make sense? So you have 1, 2, 3, 4, and let's put another 4 over here. Okay, so instead of thinking of 20 throws of a die, where exactly, if you understood the other example, this is different than the other example. Okay, in the other example, you want exactly 12 sixes, and those sixes don't have to be next to each other; they can be anywhere. Okay, this is a slightly more difficult problem. Well, not actually, it's not necessarily more difficult. It's just different. If you have 20 throws of the die and you want exactly 12, but you want them to be next to each other, if you want to only consider where the 12 sixes are next to each other, then compress those 12 rolls into just one outcome, where you roll all 12, where you roll 12 sixes in a row. Then you would say, okay, well, you can think of 9 things happening, where you roll 12 sixes in a row, and then 8 other times you don't roll a 6. Okay? And so then you can talk about the probability of you could just then say, this one doesn't really, you wouldn't have to think of this as a Bernoulli trial. So I think what's happening here is you've never studied Bernoulli trials. So I think you're visualizing a situation where you don't need it. So you don't have to use it, right? So in this situation, you don't really need it. And so I don't like this as an example in this lesson, because you're thinking of a situation where you don't really have to, by forcing them to be next to each other, you kind of don't need to use the Bernoulli function. But let me explain. Okay, so if you have 9 things happening, right? Then basically you have 9 choose 1. You're choosing 1 out of the 9 instances where you're rolling 12 sixes. And the probability of success is those 12 sixes. Well, that would be 1/6 the 12th power. Okay, that's the probability of success. That's P. P, the probability of success, is you roll 12, is 1/6 to the 12th. Wait, you know what? No, I won't even, I can't think of this in terms of, you can, but I don't want to, basically. I don't want to think of this as Bernoulli trials. So now I'm going to explain it without using Bernoulli trials. So you would then say the probability of success, you would say, well, okay, there's 1/6 chance, 1/6 raised to the 12th power, 12 successes in a row. 12 sixes in a row. And then 5/6 is the chance of not rolling a 6. And so then there's, raise that to the 8th power. And then there's just one of these guys, right? And so if there's 8 and 1, that means there's 9 of these, right? So this would be the probability of what you just said, of your situation, okay? Where you roll the dice 20 times and you roll 12 sixes in a row. That would be 9 times 1/6 to the 12th times 5/6 to the 8th. Does that make sense? I wanted to keep the conversation.
Makes sense, yes.
Oh, okay, thanks. I wanted to keep it about Bernoulli trials, but I think I explained it to you. So I wouldn't want to think of this as Bernoulli trials, because then, because the easiest way to think of this is not think of 20 rolls of the dice, compress all 12 into 1, and then I would just say, okay, 9 times, moving that one thing around. Okay, so you get it. Good. Okay, going back to Bernoulli trials, so we had all of this. Okay, so I think there are no other questions, right? Let me find the chat room again. Okay, yeah, so I answered everything, I think. Okay, good. Okay, so we'll stop there. And so next time, we will just continue where we left off. Okay, no homework. And I'll see you after spring break. Okay, have a good night. Thank you for being here. You're welcome. Good night, everyone. No, I did. I sent the exam to everyone. I said, if you haven't received the exam for some weird reason, email me and tell me you haven't. But I would say check your spam folder. Check the right email account, right? Make sure I responded to the email you sent me. Okay, so if you sent me the email, I replied back to the email that you sent the exam. So check that email account and check your spam folder. Maybe it went to the spam folder and you don't see it because it's there. If you can't find the exam that I gave back, just email me and tell me, and then I can resend it. Okay. Okay. Someone in the chat. So Hans said he didn't get it. Maybe did you check? Okay. So if you don't have it, just email me. Let me know, and then I'll send it again. Or okay, great. Okay, let me know if you need me to send it. All right. Good night, everyone. See you after spring break. Good night.